Previously, we have seen the capacity of deterministic MIMO channel. Deterministic MIMO channel. So now we will look at what is the capacity of random MIMO channel. Before that, let us first look at the capacity of SIMO and MISO channel. So SIMO basically means we have one transmitter, we have two receive antennas, and then we have links. So this can be replaced with a single pipeline. Here H would be represented as a column matrix. We have H1 and so on up to HMR. So the dimension of H would be MR cross 1. Rank is equal to 1 because we are only able to achieve one single pipeline, and thus the Frobenius norm of H would be equal to summation I goes from 1 to MR norms HI square, which is equal to lambda 1, since we have only one link. And then the capacity of SIMO would be given as C SIMO is equal to log 2 1 plus ES by N naught and Frobenius norm of H. Now, as you increase the number of antennas at the receiver side, as you increase MR, this MR will increase. So Frobenius norm will increase and capacity will increase, but the increase in the capacity is logarithmically. So even if you have CSI at transmitter, you cannot do much because you only have one transmitter antenna, and as M increases, there is a logarithmically increase in capacity. Next, in MISO you have H is represented as H1 to HMT, so it has a dimension of 1 cross MT. Again, rank is equal to 1 because here we have two transmitter antennas and one receiving antennas. So we have links, but it has single pipeline. So rank is equal to 1 and Frobenius norm is equal to summation I goes from 1 to MT HI norm square, which is equal to lambda 1. So capacity of MISO with no CSIT. When there is no CSIT, what is the best case? Best case is you send equal power symbol to all the branches. So when there is no CSIT, RSS is equal to IMT, and no CSIT, capacity of MISO would be just equal to the capacity of CISO channel, and this is even lesser than capacity of SIMO. Now when there is CSIT, what you can do, you can send the symbols with different power. So basically you control the power and you get capacity of MISO is equal to log 2 1 plus ES by MT Frobenius norm of H, and this capacity of MISO is equal to capacity of SIMO. So now what we have done, we have seen the capacity of MIMO. We have seen for MIMO we have seen two cases. When there is no CSI, the expression was in terms of lambda i's. When there was CSI, the expression was gamma I, and then we have seen for SIMO and we have seen for MISO. Again, for MISO we have two cases. When it is no CSI, capacity is equal to CISO, and when there is CSI, this is equal to SIMO. Now we will find out what is the capacity of MIMO with random channel. So we have a channel matrix H which has entries Hij. We assume that expectation of mod Hi square is equal to 1 and trace of RSS is equal to MT, which is power constraint. So MIMO setup is like this. We have antennas, multiple antennas at the transmitter, multiple antennas at the receiver. We are receiving signal, and now we want to find out what is signal received at the ith antenna, and we know how to write this expression. So we are basically writing what is the signal received at this particular antenna element. So this will be Yi. Y1 is equal to root of ES by MT HIS, which will be of dimension 1 cross MT, and then we have symbols that was transmitted from the transmitter side, plus we have some noise. So average SNR at any branch would be given by ES by N naught. And to get some insights from this random channel, what we will do, we will make some assumption. So first assumption is we assume that H is equal to spatial white matrix. And we know what is spatial white matrix, where all entries, they are uncorrelated and have equal power. Essentially, we can say the channel has no spatial correlation across antennas, and we assume MT is equal to MR is equal to M. Now the important result that we will utilize is when M approaches to infinity, 1 by M, H spatial white matrix HW Hermitian is equal to identity M. And this particular expression shows that HW is orthogonal. And we can also verify this. We can verify it this. We can write 1 by M. What is spatial white matrix? HW. We can write it as H11 and H21, so on up to HM1. Here we will have H12, we will have H1M and HMM. Now we multiply it with HW Hermitian, that is conjugate transport of this expression. So we'll have H11 conjugate. Here we will have H1M conjugate, and so on. Here we will have HM1 conjugate, and at last we have HMM conjugate. So you can basically complete this expression. So we'll try to multiply this. So when we multiply this, what we will get? We will get a matrix like this. So you have summation I is equal to 1 to M. How you write first column? You basically multiply this row. You basically multiply the first row with the first column. First row with first column, you get this element. This is H1I, H1I conjugate. Okay, this is your first element. Second element would be summation I is equal to 1 to M, H1I, H2I conjugate. So basically multiply this row, first row, with the second column. So you get this one. And similarly, the second diagonal element, you will get summation I goes from 1 to M, H2I multiplied with H2I conjugate, and so on. The rest of the terms you can easily find out, and here you have 1 divided by M. Now what is the first element? The first element is 1 by M summation I is equal to 1 to M, H1I, H1I conjugate. So you can basically write it as 1 by M summation I is equal to 1 to M mod H1I square. And using the property of law of large numbers, when M is very large, this factor can be reduced to expectation of mod Hi square, and we know this value is equal to 1. So basically this entry will be equal to 1. So this is equal to 1. Similarly, the second diagonal element would be equal to 1, and so on. So all the diagonal elements would be equal to 1. Now let us focus on the non-diagonal elements. So non-diagonal elements, we have 1 by M summation I is equal to 1 to M, H1I, H2I conjugate. So this basically reduces to expectation of HIK. So H1I multiplied with H2I conjugate, and this is equal to 0 because we have assumed spatial white matrix and they are independent. So all the entries, they are independent, uncorrelated. So this will be equal to 0. So all the non-diagonal elements would be equal to 0. So what we get in the end? In the end, we get identity matrix where the diagonal elements has value 1 and the non-diagonal elements has value 0. So we have validated this expression. And this particular expression shows that HW is orthogonal in nature. And now what we can do, in the existing expression of MIMO, we can basically replace 1 by M HW HW Hermitian, this with IM. And what is RSS? RSS is again IM. So you get, so what you get from here, you get capacity is equal to summation m I is equal to 1 to m log 2 1 plus es by n naught, which is, now the inside term does not depend on the index I, so we can basically replace this summation with multiplication m. So we get m log 2 es by n naught. So what you can see from here, the capacity is m times the CISO channel. So when we have m spatial white random channels, so when we have m spatial white random channel, and as m grows very large, we have a linear increase in the capacity. Now if m is not very large, then h is random and capacity depends on h, which is random in nature, so capacity would be random. So in that particular case, we can compute the average value of capacity for two cases, without CSIT and with CSIT. So expressions, inside expressions will remain the same, what we have studied earlier. The only thing is that you need to take the expectation over this capacity for different random channels. Now we'll look at what will happen to capacity in high SNR regime and low SNR regime. First, let us look at high SNR regime. We know the typical capacity expression of the MIMO channel. This we have studied a lot. And now with high SNR, this inside part can be reduced to simply ES by MT and not H RSS H Hermitian. And then we have a determinant and log 2 of this part. And log of product can be written as log of sum. So we can take RSS as our first part and then the other rest of the part as our second part. So you will get log 2 determinant of RSS plus log 2 determinant of MT ES by MT and not HW Hermitian. And this also we have to remember that we have the following constraint also, that means trace of RSS is equal to MT, power constraint. This will always be there. This is maximized for a given H is equal to HW, and what we get is that this expression is maximized when RSS is equal to IM, so indicating that in case of high SNR scenarios, all the branches, the symbol launched in all the branches should have the same power. And so capacity with CSIT is approximately equal to capacity without CSIT, because in high SNR scenarios, we are assuming that the symbol power would be same on all the branches. For all the symbols, symbol power would be same. So there is no impact whether the CSIT knows about, whether the transmitter knows about the CSIT or the transmitter does not, or the transmitter does not have CSIT. So this will ergodic capacity will look like this. So we have ergodic capacity, and in the x-axis we have SNR in dB. So at the very high SNR regions, the ergodic capacity basically without CSIT and with CSIT, they both basically converge to a single value, or we can say the gap is very lower. Now in case of low SNR scenarios, capacity is equal to log 2 determinant IMR plus ES by MT N naught HH Hermitian. We can decompose this HH Hermitian using eigenvalue decomposition, and we get lambda i's here. And now lambda is diagonal matrix, IMR is also diagonal matrix. Determinant of diagonal matrix would be equal to product of all the diagonal elements. And what is the diagonal elements? They are 1 plus ES by MT and not lambda I. So we can write capacity as this particular form in case of low SNR. And when we have low SNR, we need to take average of the capacity, and here lambda is replaced with Frobenius norm of H, and average capacity is determined by the total power of the channel. So that means at low SNR conditions we need to look at Frobenius norm of H. So if we try to compare this high SNR and low SNR, in high SNR scenarios, what we need to do, we need to take RSS is equal to IM. So power across all the symbol is same. In case of low SNR scenarios, for capacity, we will look at Frobenius norm of H.